Good morning to all. This is Dr. Shivam Mishra, and I'm here to deliver a lecture on vapor compression refrigeration system. So, first of all, we would read about what is a vapor cycle. First of all, we would read about what a vapor cycle. Vapor cycle is that in which the refrigerant undergoes at least a one time of change during the heat exchange process. If we'll go, if we read about the vapor cycle, we can classify it into three parts, that is vapor compression cycle, vapor absorption cycle, and vapor jet refrigeration cycle. In most of the cases we use vapor compression cycle because it is suitable for most of the devices ranging from few watts to the capacity of few megawatts. So we will study the vapor compression cycle because it is most widely used in most of the refrigeration cycle. The basic that we will start is the Carnot cycle, which is the base of vapor compression cycle. Carnot cycle, which is the base of the vapor compression cycle, and these are the components of this vapor. These are the components of the Carnot cycle. It includes a condenser, a compressor, an expander or a turbine, and then an evaporator. Evaporator is that part in which the refrigeration effect is produced. The refrigeration effect, how it is produced? When a heat exchange is taken place between a refrigerant and the confined space, the refrigeration effect is produced. It is also known as, this part is also known as heat source, while this part where heat rejection takes place is also called as heat sink. So here in case of Carnot cycle, that is reverse Carnot cycle, which is the base of vapor compression cycle, condenser is known as heat sink, while evaporator is the heat source. These are the streams of the reverse Carnot cycle. It consists of 1 to 2, that is the process of compression, which undergoes into the most of the time we use reciprocating compressor. 2 to 3 is the heat rejection process that takes place into the condenser or the heat sink, where as expansion takes place into the turbine, that is the process 3 to 4, and 4 to 1 is the evaporation process where the refrigeration effect is produced. If we will represent this one on TS curve, that is temperature entropy curve, the process, the curve which is shown in the form of vapor dome is the left hand side. This line, this is the critical point, and this line is known as saturated liquid line, while the curve on the right hand side is known as saturated vapor line. Now, if we'll relate this schematic diagram of a reverse Carnot cycle to this TS curve, we'll get 1 to 2 is isentropic compression, while 2 to 3 is constant temperature, that is isothermal heat rejection, which takes place into the heat sink, while 3 to 4 is isentropic expansion process, which takes into the turbine part, while 4 to 1 is the constant temperature or isothermal heat absorption, which takes place into the evaporator part. Will represent the heat rejected as Q out, while the heat input into the evaporator part is will represented by Q in. Now also, before we proceed, we will have a convention, sign convention. We should know that if it is a system and heat is being added, if heat is being added, we'll represent it as a positive, while if heat is being rejected, we'll represent it by negative, because heat rejection is obviously a negative process. Well, if work is done onto the on the system, if any system undergoes a work and it is the work is done on the system, we'll take it as negative, while which is happening in case of the isentropic compression process, while if the system itself does the work, then the sign convention will be positive. So we'll derive a formula for CUP of this reverse Carnot cycle. Now we all know that from the first law of thermodynamics and second law of thermodynamics, we'll relate this one to derive this formula. We'll get that from the first law of thermodynamics, we know that cyclic integral of heat transfer is equal to cyclic integral of work transfer in a system. We'll represent it by equation number 1. Now, where the heat is being transferred, the heat is being added into the evaporator part, while it is getting rejected into the condenser part. So del Q will be Q 4 to 1, which is a positive obviously because the heat is being added, while process 2 to 3, which is a heat rejection process, when it goes into the condenser, the heat is being rejected. So it will be a negative because heat is getting rejected. So we'll represent del Q is equal to Q 4 minus 1, 4 to 1 minus Q 2 to 3, that is the heat rejection process. This one is the heat rejection. This takes place into evaporator and we'll represent it by QE, while the heat rejection takes place into the condenser and we will represent this one by QC, that is a condenser. Also we know that in the compressor the work is being done on a system, while in the expander or turbine the work is being done by the system. So the positive work is in the expansion part. So del W will be represented by work of turbine minus work of compressor. Because why this is negative? Because work is being done on the system, so compressor work will always be negative, while the work is being produced into the turbine, so this will be always a positive quantity. Now we know that from the equation number one that integral of del q is equal to integral cyclic integral of del w. So when we'll equate this equation number 2 and equation number 3, we'll get QE minus QC is equal to WT minus WC, that is negative of W net. What is W net? W net is the work which is being done on the system, overall network which is being given as an input to the system. So we have this formula QE minus QC is equal to WT minus WC, that is W net. From second law of thermodynamics, we know that heat transfer is equal to integral of TdS, that is if heat is being rejected or heat is being added, we can represent it always into the terms of temperature and the terms in the entropy change form. So where the heat is being rejected, it is the process 2 to 3 and the heat is being added into the evaporator process, that is process 4 to 1. So if I will write that Q 4 to 1, which is the QE part or heat is being added, we can represent it by T, that is the temperature of the evaporator, which is constant over here, as 4 minus S1. While if I'll write Q2 to 3, which is obviously the heat being rejected, we can represent it as temperature of the condenser, which is constant. Obviously this the heat rejection process is the isothermal heat rejection process. We can represent it as by S2 minus S3. But since this is a heat rejection process, since this is a heat rejection process, we can write it as S3 minus S2. Negative of heat rejection will be negative of this heat rejection will be S3 minus S2. Now we also know that entropy remains constant during the compression as well as the expansion process. Entropy remains constant during the expansion as well as the compression process, that is S1 is equal to S2. We can see it from the curve because this is the isentropic compression process. Also S3 is equal to S4, that is entropy remains constant during the isentropic compression process. So we can reach at a conclusion that COP of any refrigeration system is represented as refrigeration work divided by the net work input to the system. And if we'll write the formula, we can write it as what is the heat rejection process, heat addition process, that is in the refrigeration effect is obviously into the evaporator part, that is T S1 minus S4 divided by TC S2 minus S3 minus TE S1 minus S4 part. This one gives the net work input to the system. Now if we'll put these values over here, we can reach at the conclusion that COP of a Carnot cycle, which is obviously a reverse Carnot cycle, is the function of TC and TE. If we'll put this values over here, it will get cancelled and it will be in terms of T divided by Tc minus T. So we'll reach at a conclusion that COP of a reverse Carnot cycle is obviously the function of condenser temperature and the evaporator temperature. It means a reverse Carnot cycle, for a reverse Carnot cycle, the COP is the only function of operating temperature, that is Tc, condenser temperature, and evaporator temperature, which is also the heat sink temperature and the heat source temperature. One more conclusion we can draw, that COP of a reverse Carnot cycle does not depend on the working fluid of the cycle. It is obviously the COP of the Carnot cycle is independent of the what working fluid we are using, whether we are using the R11, whether we are using R12 or NH3 or carbon dioxide, whichever refrigerant or working fluid is being used, it is independent of that all. One more conclusion we can draw, that for a given temperature limits, if we have a fixed heat source temperature, if we have a fixed heat sink temperature, none of the cycle operating between the same temperature limits, none of the cycle can have the better COP as compared to the Carnot cycle. If operated between the same temperature limits, none of the cycle which is being operated between the same temperature, none of the cycle can have a better COP as compared to the Carnot COP. Now the question comes, if it is so that any system cannot have a better COP as compared to the Carnot cycle, why are not we using this Carnot cycle, reverse Carnot cycle? It means, what are the practical difficulties? What are the practical difficulties while adopting this reverse Carnot cycle for a refrigeration purpose? These are, first one is the wet compression. The first problem is that wet compression process. Here we can see the point 1, which is the inlet to the compressor, is always into the two-phase region. It means it consists of the liquid plus vapor. Since it is into the two-phase region, it has liquid as well as the vapor particles. So when the compression takes place, which is isentropic compression into the reciprocating compressor, it is always causes a problem to the compressor. Compressor cylinders, its heads can get damaged. So we have a problem that wet compression is the major flaw of this vapor compression, this reverse Carnot cycle, because it can damage the cylinders and its head. The second difficulty which we will face during the expansion process. We have used turbine for the expansion. At the end of the condensation process, we have the saturated liquid, which is represented by the point 3 on the TS curve. We can see it here. The point 3 is the saturated liquid. I have already told you that left part line is saturated liquid line and this one is a saturated vapor line. The point 3 lies on the saturated liquid curve, so it is a saturated liquid. So when the expansion process takes place in the turbine, we know that for a turbine or for an open cycle, the work is given by integral of VdP. Since we know that volume of the liquid is far less as compared to the volume of the vapor, and we have to expand the liquid part, and for the same pressure difference, that is for the condenser pressure and for the evaporator pressure, between these two pressure limits, the work being produced is very small, which is obviously a positive work because turbine is a work producing device. This work is very small as compared to the work being consumed into the compressor part. So it is not justified to use a turbine uh, for the expansion process, which obviously produces a positive work, but this work of turbine is very less in comparison to work being consumed or work being given input to the compressor part. So these are the two practical difficulties which we face during the reverse Carnot cycle. That's why it is used as an ideal cycle, and it is used for the comparison purpose of other vapor compression or vapor absorption cycles. Now we come to the point vapor compression refrigeration system. So we have studied the reverse Carnot cycle. Now we come to the point vapor compression refrigeration system. What are the deviations? Why we have adopted this vapor compression refrigeration system rather than adopting the reverse Carnot cycle? So what are the deviations? The deviation we will get in terms of expansion, it will be always different than the reverse Carnot cycle. In terms of heat rejection, in terms of heat addition, will have some differences. So let me draw the schematic diagram of. Rather than using a expander over here, we'll use a expansion device, that is a throttling valve in vapor compression refrigeration cycle. All the components, all other components will be same. There will be an evaporator, a compressor in which the isentropic compression takes place, condenser in which the heat rejection takes place, and expansion device. A throttling valve is being used in place of a expander over here. So what are the differences? We'll represent it by a TS diagram. Here we can see the process 1 to 2 is isentropic compression. The compression process remains same as that in case of reverse Carnot cycle, while process 2 to 3, in that case the process 2 to 3 was constant temperature heat rejection process, while in this case, in case of vapor compression refrigeration system, the process of heat rejection, that is 2 to 3, which takes place in the condenser, isenthalpic expansion. And again, the process 4 to 1, which takes place in the evaporator, it is the where heat from the confined space is consumed for evaporation of the refrigerant, and refrigeration effect is produced. So the process differs. 1 to 2 remains same, which is isentropic compression. Enthalpy remains constant during this process. 2 to 3 is constant pressure, heat rejection. 3 to 4 is isenthalpic expansion, which takes place in a throttling valve where enthalpy remains constant, while 4 to 1 is constant pressure, heat addition, which takes place process 4 to 1. So these are the major differences. We have replaced this constant pressure, heat rejection in this by the constant temperature heat rejection in case of reverse Carnot cycle. While enthalpy was constant during the expansion process in the reverse Carnot cycle, while entropy was constant during the expansion process of a reverse Carnot cycle, while enthalpy is constant in this process. So these are the modifications. Now we'll compare the reverse Carnot cycle with vapor compression refrigeration cycle on a TS curve. Comparison will be shown on the TS curve. We can show it itself. Now, the cycle 1, 2, 3, 4, 1, 2, 3, 4, which is shown here, is a VCRS cycle. 1, 2, 3, 4 is the VCRS cycle, while process 1, 2 dash, 3 and 4 dash is the reverse Carnot cycle. When we will compare this one, we can see first point is that the refrigeration effect decreases in case of VCRS cycle in comparison to the reverse Carnot cycle. We can see the refrigeration effect decreases. Now here we can see that in case of VCRS cycle, we have the points 1, 2, 3 and 4. This is obviously a isenthalpic expansion. This is irreversible. That's why shown by a dotted line. So we can see this portion, the point 4 and 1, that this portion drawn by the hashed line is the refrigeration effect in case of VCRS cycle, while the area 4 dash 4, 4 dash A, B and 4, this extra area will also be added in case of reverse Carnot cycle. So we can see from the TS curve that refrigeration effect decreases in case of VCRS cycle in comparison to the reverse Carnot cycle. Refrigeration effect decreases for vapor compression cycle versus, if I'll compare this one to the reverse Carnot cycle, the refrigeration effect is decreased. Again, we can also compare it in terms of the work addition or the work input to the compressor. We can again show it. We can again show it on the TS curve. 1, 2, 3, 4 is the vapor compression refrigeration cycle, while 1, 2 dash, 3 and 4 dash is the curve for a reverse Carnot cycle. If we will compare this one for area under the curve for a vapor compression refrigeration cycle, while for the reverse Carnot cycle, we can see the work input for the reverse Carnot cycle is represented by the hatch line, which I have shown, that 1, 2 dash, 3 and 4. This is the work input to the compressor in case of reverse Carnot cycle. While for the vapor compression refrigeration cycle, we have area, this extra area is also being added, and it is known as superheating horn. Area under the curve always gives the work and work for the work input to the system. So for a vapor compression refrigeration cycle, we have also this extra area, that is, we also know it as throttling loss. So we can see here that one work input to the compressor in case of VCRS cycle is greater in comparison to work input to the compressor in case of reverse Carnot cycle. Also, we can see that in case of VCRS cycle, the heat rejection, the heat which is being rejected is also in a larger amount in comparison to the heat which is being rejected in case of reverse Carnot cycle. So this is the comparison part of the vapor compression refrigeration system. Now we'll discuss the standard single stage VCRS cycle. A standard single stage VCRS cycle. It is also known as SSS. We call it as SSS because it's standard single stage VCRS cycle. Here, what are the modifications? What are the modifications in comparison to the reverse Carnot cycle? And we can see there is a condenser, there is a compressor, Again, there is a expansion device and a evaporator. If we want to derive the COP of this standard single stage VCRS cycle, we'll have to go through the individual components. We'll have a steady flow. We'll apply the steady flow energy equations for the all the components which are the part of this, and we'll get the formula of COP for this standard single stage VCRS cycle. First of all, we are taking the evaporator. Evaporator is a heat exchanger. Here heat addition takes place and the stream 4 is being entered and the exit is stream 1. Since it is a open cycle, open system, we'll apply the steady flow energy equation here. But before we can apply the steady flow energy equation, there are few assumptions we'll take care during deriving the COP equation. That is, the kinetic and potential energy will be neglected. There will not be any pressure loss or heat loss during the arrangements, during the pipe arrangement. There will not be any pressure and heat loss. Also, all the components are under steady state condition. So, if we'll apply steady flow energy equation, we have H4 plus heat is being given plus Q in is equal to H1, because there is no any work transfer, there is no any loss is considered, and kinetic and potential energy are already neglected. So heat addition into the evaporator part is given as formula H1 minus H4. That is again the refrigeration effect. Now if we'll apply this again steady flow energy equation to the compressor part, the work is given as an input into the compressor, while the streams which are being entered is stream 1 and which is getting out is is stream 2. So if we'll write this steady flow energy equation, H1, that is the enthalpy at point 1, is plus, since the work is given input, WC is equal to H2. The work of compressor is represented as H2 minus H1. Again we have the condenser, in which heat is getting rejected while streams are 2 and 3. The stream 2 is getting entered into this condenser and the stream 3 is the exit stream. So if we'll apply, we'll get H2 is equal to QR plus H3. Enthalpy at point 2 is equal to heat which is being rejected plus enthalpy at point 3. So the value of heat rejection is given as H2 minus H3. Again we have the throttling valve. in throttling valve the enthalpy remains constant. It is an isenthalpic expansion process, hence H3 is equal to H4. So COP of a refrigeration system is given as COP of VCRS cycle will be given as refrigeration effect divided by work input to the compressor. The refrigeration effect we have find out as H1 minus H4, which is produced in the evaporator, while work input to the compressor is given as H2 minus H1. As we applied the steady flow energy equation into to the compressor part, we have got this values. So here we can see, if I have represented this COP of the vapor compression and refrigeration cycle in terms of enthalpy, if we have H1 minus H4 divided by H2 minus H1. If we try to solve any numerical based on this, and if we know the values at the end point, that is entry to the compressor, exit to the compressor, exit to the condenser, that is saturated liquid, and exit to the in throttling valve, that is point 4. But if we'll know the value of enthalpy at saturated liquid line, which is obviously at the exit of the condenser, we have H3 is equal to H4, because in the throttling valve the process is isenthalpic expansion process. So for solving this, if we know the enthalpy at this point, which will obviously be the enthalpy at the dry saturated line, that is represented by Hg. If our point lies in two phase region, then how we will calculate? If it lies in two phase region, which is represented by 1 dash, 2 dash, 3 and 4, how we will calculate this one? Since this is the isenthalpic compression process, so we must be knowing the the entropy at point 2, which is 2 dash. It may also be happen that we do not know the entropy at this point, and we will have to calculate through the using the steam table. And if we know this one, then how we will do? S2 dash will be equal to S1, because entropy remains constant. Now we have the problem is how we will calculate the point enthalpy at point 1 or 1 dash. If we know this one, we will equate and we will get the dryness fraction at point 1. If we will equate this one, we will get the dryness fraction at this point, because we know the value of S2 dash. If we know the value of S2 dash, we know from the steam table we can read the value of SF, which is entropy for a liquid at this evaporator pressure line, and this SFG is the entropy for the two phase region or the vapor dome region. This is also the difference of Sg minus Sf. So we can calculate this dryness fraction value over here. When we calculated this value, dryness fraction, now we can calculate the value of H1 dash by using, since we know the enthalpy at this saturated liquid line, which is represented by, let us say, HF, plus now we know this value, dryness fraction, plus X SFG, X HFG. HFG is the enthalpy of vaporization. We can read it directly by the steam table, or if our point lies at point 1, which is saturated, dry saturated line, we can directly read the value Hg from steam table. The, the value at point 3, the value of point 3, which is enthalpy of point 3, can be calculated directly from the steam table. That at the, we'll have to do that at the condenser pressure, we'll have to read the value of saturated liquid directly. So enthalpy of the saturated liquid we can read. So we know, now we know the value H3. Now we know the value H3, and since we know that expansion process is isenthalpic, we have H3 is equal to H4 because enthalpy remains constant during the isenthalpic expansion process. Now we know all the values H1, H2, H3 and H4. So from the formula we can calculate COP of the VCRS cycle, or a standard single stage cycle is calculated as refrigeration effect divided by work input to the compressor, that is H1 minus H4. Refrigeration effect, we have calculated this one. We know the value H1 and we know the value H4 because we know the value of H3, and this is H2 minus H1. So from this lecture we have concluded that COP of the VCRS cycle can be calculated like this. We can